Hello all. This video is going to cover everything in this packet here, which is in the class 13 folder. So for those of you that were present in class for class 13 and don't feel like you need a review of the parts that we did so far, look in the section under the video on YouTube. I'm going to put the timestamp in case you want to fast forward and just start right where we left off in class. But if you do want a review, I'm going to restart this handout. So here we go. Okay, so at the top of the class, we did these math nows. Okay, so starting with math now 1, right? It tells you to find area under the curve under the given interval. This one is shaded in, whereas this one you would have to shade in yourself. When we say area under the curve, we mean the area between the function graph itself. So we keep saying curve. In this particular example, it's a line. So we mean the space between the function graph itself and the x-axis. And then we have this note here that's going to come into play later. If a curve goes under the x-axis, that area is negative. So just keep that in mind for later. Okay, so the first graph here is a triangle. The base is 2, the height is 2, and the area of a triangle is half times base times height. Half times 2 is half times 4. Half times 4 is 2. So the area of this shape between the line and the x-axis is 2. And then over here, we have this exact shape. Again, so we already know that part's 2. And then we have a unit and a unit. 2 plus 1 plus 1 is 4. All right, so then we were about to move on to part 2, but we decided that we wanted to do a quick Riemann sums review in class. And so I'm going to show you some of the Riemann sums answers from the homework. So the homework, this is from your class 12 packet. So page 9 of your class 12 packet shows this. And we talked in class about how unfortunately there was a typo. There was supposed to be a 2 there. So very sorry about that. However, that was kind of a blessing in disguise, because what I really want you all to understand is that Riemann sums is about estimation. So you could use this chart to get exact values, but what's even more important for you to understand about Riemann sums is just looking at the graph and estimating. So I'm actually going to skip past this little part and just review these problems. So we can see here, it says approximate the area on 0, 3, so from here to here, using 3 left-bound rectangles. So because this is 3 units long, 3 divided by 3 is 1. So we know that each rectangle is going to be 1 unit wide. So I'm just going to draw these little purple guidelines to show the start and end of my rectangles. Because this says that it's left bound, I'm going to start tracing my curve. And when I hit one of the purple lines, I'm going to draw a line from the left over to the next one. Then I'm going to just follow the purple line up. I hit the curve, draw a line from the left over to the next purple line. Up again, I hit the curve, over to the left, and I hit the next purple line. So those are my 3 rectangles. The first one is flat, so it has an area of 0. The second one is, if I look up here, it's 2 tall, and the base is 1, so 1 times 2 is 2. And then over here, 1, this is 3. 1 times 3 is 3. So there was a typo, that's all right. So 0 plus 2 plus 3 is 5. So we have an approximate area of 5 here. Let me show you the right one to kind of keep going. I'm going to go through all of them. So it's your choice if you want to watch the whole video or fast forward, depending on how your comfort level with Riemann sums. Okay, so for the right, same idea. We already know that the interval is 0, 3. There's 3 rectangles. So the first step, if the rectangles are here, let's pretend they're not for a second. The first step would have been to draw some purple lines in just to show where the start and end of the rectangles are. And then trace the curve. And now because it's right bound, I'm gonna trace. And then when I hit this point, I go from the right, like so. Trace from the right. I guess I really should have just been coming from the right. That would have been wiser, but that's all right. And then down here. So like if I was coming from the right, boom, up, coming from the right, boom, coming from the right, boom. So now I have, this is 2 tall, this is 3 tall, this is 0 tall. So it's again 5. So sometimes, very frequently, there'll be the same answer. It's only when it's like a very unsymmetrical graph that you get some very different answers. Okay, midpoint is a little bit more difficult. So I'm going to do what I did in class, which is show this as a guide for midpoint. Okay, so here we are. We are going to fill this out. This is in radians. We grabbed our calculators and we plugged in what sine of pi over 12 was. These are the values that we got when we plugged into our calculators using radian measurement. We know it's radians because we see the pi sign. We also made some discoveries about, since this part of the sine graph is symmetric on this line, we saw repeating values. Okay, so directions say to draw 6 midpoint rectangles. So I'm going to pause. 6 rectangles. 0 to pi is our interval. So the rectangles have to be evenly spaced. So pi divided by 6 is going to be how wide each rectangle is. So step 1, similar to what we did on the other page, is to draw these guidelines in. And these guidelines are here to show where our rectangles are going to start and end. Now, if it's a midpoint rectangle, you have one extra step because you're not going to be coming from the left or the right. You're going to be on the midpoint. So the extra step is to then draw some midpoint lines in. So I am showing where the middle of the rectangle is. Okay. Now I start tracing, and when I hit that midpoint line with my curve, that's the top of the rectangle. When I hit that midpoint line with my curve, that's the top of the rectangle. And so on. And so on. And so on. And so on. Okay. Cool. Now we want to find the area, right? So we could approximate it, or we can just use these values that we found. Okay, so this first rectangle, right? We know it's base times height. The base is pi over 6. That's how wide it is. And the height, we know, because we plugged it in, is 0.26. You also might have just looked at it and said like, oh, it's 0.25. That's fine. Again, Riemann sums is about estimation. The next one, again, every single one of these is going to have a width of pi over 6. And then this height we know is 0.71. Cool. Next, the width is pi over 6. The height is 0.97. And then this graph happens to be symmetrical, so the next one is same. The next one is the same as that one. And the last one is the same as this one. Okay, so interesting thing here. Every single one of these got times by pi over 6. So to make our lives easier, we should just factor that out. Add up all these numbers. And then whatever we get when we add them up, we're going to times by pi over 2. In class, we said that was around 2. Some of us got 203, some of us got 204, some of us got 2. Again, Riemann sums is about estimation, so there's no perfect answer. If you happen to encounter one of these on the CST, it's going to be multiple choice, and you will just pick the multiple choice that's as close to your estimate as possible. Cool. So that's an example of the midpoint Riemann sums. I'm also going to show you, I'm going to move this. I'm also going to show you my filled in page 10. Here we go. And you'll see in the folder, Miguel's work for this page is also in the folder, and it's perfect work, so check it out. So again, this is our left bound. You can see that the rectangles are coming from the left. This is our right bound. Rectangles are coming from the right. And this is our midpoint. And you can see that the middle of the rectangle is on the curve. Cool. So that's page 10. Also going to show you my page 11. So this one, it said to use 12 rectangles from 0 to 3. So that divides 3 units into rectangles that are 1/4 units wide, or 0.25. Left comes from the left. Right comes from the right. And last but certainly not least, here's page 12. Whoops. Not sure what's going on with my camera. Okay, so here is my page 12. So now we can see the midpoints. And again, the idea here for making this picture is you trace these purple lines first. The purple lines showed where the rectangles were going to start and end. And the dotted lines, this is the extra step for when it says midpoint. The dotted lines are where the midpoints are. And then as you trace your pen or pencil over your curve, once the curve intersects the dotted line, that's where you draw the top of your rectangle. And then you find the heights of all 12 of these rectangles and then multiply it by the width. In this case, it was 0.25 each. And it came out to something around 5. Okay, cool. So that's Riemann sums review. And now I'm going to transition back to this packet. We did the front page already, and now we're going to move on to page 2. Okay, so let's talk about all these numbers. Okay, so this is the packet that we filled in class. So let me show you how we got there. All right, here we go. Okay, so we started by finding the derivative. Okay, so what's the derivative of this? We're going to use power rule. 3 times 4 is 12. 3 minus 1 is 2. Here, the power is 1. It's going to go down by 1. It's going to be x to the 0, which is just 1. Here, 2x. Here, 6x squared minus 2. Back in, I think it was class 5, we learned about these 4 derivatives. Oh, I also had given a direction to cross this one out. You don't need this box. So these 4 derivatives we discovered a while ago. We know that the derivative of sine is cosine. And when I say discover, I mean that we had in class taken the time to actually find tangent lines to the curve of sine, and then discovered that it created a graph of cosine. And we did the same thing for these 4. So it's not just like a random thing, it's an actual mathematical reasoning and discovery. So derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of e to the x is itself. And derivative of 1 over x is ln of x, also known as the natural log. Don't be too stressed about these two. They're just good to know, but we're not going to see them too frequently. And you won't see them on the final. Okay, so continuing on. Now, super important. This is the kind of last giant idea that you're going to learn for this class. You've been doing derivatives. We're going to talk about the antiderivative, the opposite of the derivative, also known as the integral. Antiderivatives and derivatives are inverses of each other. So you're doing the reverse. So here we see this integral symbol, which also means antiderivative. So now we want to go backward. What function would have this derivative? Well, we know that the power should go up by 1, x to the 4. And then let's see, if I did the derivative, the 4 would jump in front, and this would go down by 1, which is exactly what's right here. So this is the antiderivative of this. Okay, here, we know the power should go up by 1. But the 2 is going to jump down, and I don't see a 2 here. So what would have needed to be here that I could times by 2 that would give me 1 half? Okay, here, we know that it goes up by 1. There's nothing here. The 3 is going to jump down. What would I need to times 3 by to get me that 1? 1/3. Here, this 3 used to be a 4. What would I have needed to times the 4 by to get me a 2? Well, half of 4 is 2. For this guy, the minus just comes over. X is to the 1 right now, so that means it used to be to the 2. 2 jumps to the front. Okay, 2's there, so that works. 3. If I do 3x, the 1 will become a 0, which just means 3 times 1, and that's what I have here. Perfect. Sine of x. So let's think about this critically for a minute. The derivative of cosine was negative sine, but this is positive sine. So this must be negative cosine. So let's check if that works. The derivative of cosine is negative sine. The derivative of negative cosine will be negative sine, also known as positive sine. Sounds good. Okay. What's the antiderivative of cosine? Well, the derivative of sine was cosine, so this has to be sine. Excellent. All right. Derivative of e to the x is just e to the x, so the antiderivative is also just e to the x. Okay. So that is antiderivatives, which we're going to be practicing more as we continue this packet. Okay. Da, 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 da. All right. Fundamental theorem of calculus. Part 1 is on page 2, and part 2 is on page 3. So take a look. The fundamental theorem of calculus, as usual, is stated in very scary notation language, but it's actually saying something very simple. It's simply saying that the derivative and the antiderivative are inverses. That's all it's saying. And it's also saying, like, when you use this symbol, like when you integrate a derivative, you'll get the original function. Sometimes you're going to know what A and B are. So for example, in the math now, we knew we were going from 1 to 3, but you won't, or 0 to 2. You won't always know those values. So when you don't know those values, your answer is just going to be an algebraic expression, and you'll need a plus C. Here's why. We go up to this table, right? We see that there was plus C's all over. Think about this. What is the derivative of just a number? Derivative of 1, for example. Well, that's just 0. Derivative of 9, derivative of 1,000,000. All derivatives of constant numbers are just 0. We have no way of knowing what was added, or if it was just a 0 that was added, which is still a constant. So that's why we always put a plus C, because we do not know what constant existed at the end of the antiderivative, because the derivative of any constant is just 0. So when you don't know A and B, when you don't know your interval, and you're just finding a generic antiderivative, you have to put a plus C at the end. Now, there are times, fundamental theorem part 2, there are times where you will know A and B. And that is what we're going to talk about right now. So when you do know A and B, you can find an exact value because you can plug in. So whenever we're doing antiderivatives, what we're actually doing is finding the area under a curve. So we're going to do this example. We're going to do the math now example. In the math now, we had the graph of f of x equals x, and we were doing the interval 0 to 2. So the way that would look calculus-wise is like this. Integral of x from 0 to 2 with respect to x. I'm going to say that again. This is what dx is, like the end parenthesis. The integral is like the open parenthesis. So the way you read this mathematically is integral of x from 0 to 2 with respect to dx. The way you do that is you find the antiderivative. This little line with the 2 and the 0 just means evaluate. This is just you showing work. No stress about using this symbol if you don't want to. Then you're going to plug in. You're going to plug in the upper bound minus plug in the lower bound. So the upper bound was 2. We plugged that in here. 2 times 2 is 4, times half is 2. Minus, this all becomes 0. Our answer becomes 2. So we just used calculus. We used the fundamental theorem of calculus part 2 in order to find the area under the curve from 0 to 2 of the function x. We got the answer of 2. And if we look at our math now, we said the area under this curve was 2. So we are correct. Cool. All right, so now we're going to try this one. We want to find the integral, the antiderivative, the area under the curve, 3x squared, from 1 to 3 with respect to x. So the first thing we're going to do is find the antiderivative, which means the power goes up by 1. And just to double check our work, if we were to derive this, we would get 3x squared. Perfect. We are going to evaluate this, evaluate from 1 to 3. That's going to look like this. Plug in the upper bound, plug in the lower bound. 27 minus 1 is 26. That's our answer. We're done with this problem. Just to give you a visual, what you have just found is, let's say you were to graph the function y equals 3x squared. It would look something like this. It would be a parabola, right? No, that I didn't really draw it well, but it's a parabola. And you're finding the area under the curve from 1 to 3. So you just found that this area under that curve between 1 and 3 is equal to 26 units. That's what you've discovered. Cool. Okay, this is where we got to in class. So for those of you that had fast forwarded, welcome back. And now we're going to finish the entire packet. So please make sure that you carefully follow along for the whole rest of this video, because this is your final lesson, final pieces of new information, before you just dive into the review packet. Okay, so here we go. So for number 2, this is a definite integral, and the reason it's definite is because we know the upper and lower bound values. If we don't know them, they're called indefinite. Okay, so let's try this out. So the antiderivative of sine. Well, we could think about it, or we could just flip to our cheat sheet, and it says that the antiderivative of sine is negative cosine. Okay, cool. So we are going to evaluate the antiderivative, which again, we said was negative cosine, from 0 to pi. Okay, so negative cos minus plugging in. We're maybe not sure. We could just draw our little cheat sheet on the side to remind ourselves that cos of pi is -1. But don't forget, there's already a negative sign here. And cos of 0 is 1. Cool. All right, let's deal with these negatives. These come together to give us 2. So what have we just discovered? We now know that the area under the curve of sine from 0 to pi is equal to 2. I'm going to say that again. We now know that the area under the curve of sine from 0 to pi is 2. Well, that's interesting, because if you go to page 1, this is sine from 0 to pi, and our Riemann sums estimate was so close to 2. So we're pretty amazing. Cool. All right. Moving right along to number 3. All right, so we're going to evaluate. By the way, if you, as you're doing this video, it would be cool if you wanted to pause it and like try these on your own and then watch to check if you got it right. That would be a good study practice. Okay, so we're going to try this one. This one is just a constant. So we are going to evaluate it from -3 to 3. The antiderivative of 2 is just 2x. So we're going to have 2 times. We're going to plug the upper bound of 3 in and the lower bound. 6 minus 6 is 12. Cool. And then if we wanted to check our work, you don't have to, but if you wanted to check your work, what you could do is you could sketch yourself a graph of the graph of y equals 2 from -3 to 3. And we can see visually that this is indeed 12 units. So we did it right. All right, moving right along. Again, feel free to pause and do the problems and then unpause. We're going to evaluate the antiderivative from -2 to 1. So it's going to be x to the 4th. And the only thing that we could times 4 by to have a 1 in front would be 1/4. We're going to do 1/4 of the upper bound to the 4th minus 1/4 of the lower bound to the 4th. Upper bound, lower bound. Okay, so that gives us 1/4 minus -2 times -2 is 4, times another -2 is -8, times another -2 is 16. 16 times 1/4 gives us 4. So this is going to be -3 3/4. Cool. So this is the answer. And then again, if you just want to check your work because you're more of a visual person, what you could do is you could sketch the graph or just look in Desmos. This is the graph of x cubed from -2 to 1. And so a reminder that if it's under the x-axis, this is all a negative area. And if it's over, it's positive. So we can see that this negative area is bigger than the positive area. And so it makes total sense that our answer would be negative for this one. Cool. All right, moving right along. Okay, so number 5. Had to throw some challenge problems in here. Okay, so for number 5, we are gonna same old thing, right? We're just going to evaluate. And we know that the antiderivative of 1 over x is ln of x, and we know that from our cheat sheet back on page 2. So now we plug in, so ln of the upper bound minus ln of the lower bound. So it was e to the 2 and e. And you may or may not recall that ln of e, ln and e are inverses of each other, which means ln of e is 1 and ln of e to the 2 is 2. 2 minus 1 is 1. So that's just a fun challenge problem. If you're not, what's the word? An expert on ln's and e's, please don't worry about it. Ln and e is not going to be on our final. It's something, good to know for like the Algebra 2 curriculum. You're going to need natural logs and e's. But don't be too stressed if you don't know what the heck this is. That's not something to be stressed about. Okay. Same deal here. We are going to evaluate. We know the antiderivative of e to the x is still just e to the x. E to the 1 minus e to the 0. Anything to the 0 is 1. This is just e. I would honestly just leave it as e minus 1, but you could always grab a calculator and find the whole decimal value. E is an irrational number. It's going to go on forever. I think it's good to just leave it there. So those are just two kind of extra practice to kind of show you how you can bring in some other stuff, but don't be too stressed if you didn't understand 5 and 6. Okay, for the challenge one, so this is just to kind of get you thinking about how integral means area under the curve. So it would be really cool if you paused and tried this before you unpause, because I'm about to reveal the solution. So it says using only a graph. Okay, so sine. I'm going to sketch a graph of sine from 0 to 2 pi. And here, it's testing that I understand that integral means area under the curve. So this in blue and this in mint, those two pieces are the exact same amount of area, One of them is above the curve and one of them is below the curve. So they cancel each other out. So that means that the area under the curve of sine from 0 to 2 pi is actually 0, because this area and this area cancel each other out. We don't need to know what the area is. We do know, because we did it in number 2. We know that this is 2, which means this has to be -2. But the important thing to know is they're exactly identical, so they cancel out. So this area, this integral, equals 0. And then if you were to graph tan looks like this. There are some asymptotes, but we purposely used numbers where we haven't hit the asymptote yet. So we would have an area here in blue and an area here in purple. And those are exactly the same because tan is symmetric. We don't even need to know what these values are. We just need to know they're the same. One is below the curve and one is above. So they cancel each other out. So the area under the curve, also known as the integral of tan from -π3 to π3, is 0. Cool. Okay. So we just did a bunch of problems where we could find a clear numeric answer. Now we're going to talk about indefinite integral. So that's when you won't see an upper or lower bound, where you don't know the answer. Or I'm sorry, you don't know the interval. And so that means that your answer is going to be in the form of an algebraic expression, and you need to remember the plus c. So for 7, what is the integral of cos? Well, all you need to do is find the antiderivative, which on page 2, we said the antiderivative of cos was sine. So the answer to this problem is simply sine of x plus c. Done. That's all you got to do. For this one, we want to find the antiderivatives of these 4 pieces. So we know the power goes up by 1, 4 jumps to the front. Okay, that one's done. Up by 1. The 3 is going to jump to the front. What could we have times 3 by that would have given us 2, though? I'm going to say that again. What could we have times 3 by that would give us 2? 2/3. Next. Exponent goes up by 2. Sorry, 1, becoming 2. What could I have times 2 by that would give me half? So you'll notice a lot of fraction practice required with these integrals and antiderivatives. Bringing the constant down, it had to have been a x. And then last but most certainly not least, don't forget your plus c. This is your answer. There's nothing to plug in. It's an indefinite integral. This is your answer. Cool. All right, number 9. Oh, okay. Negatives look tricky, but we can definitely handle it. So as a reminder, when you're anti-deriving, your exponent goes up by 1. So -2 plus 1 would be -1. So I have x to the -1. And then this would jump down, putting a negative in front, which it is. So this is the answer. If you wanted, you could rewrite it as a 1 over x, because that's what the negative exponent means. But you cannot forget the plus c. So again, let's just check our work. If I was taking the derivative of x over 1, or also known as x to the -1, -1 would jump to the front, and -1 would be decreased by 1, giving us a -2 with a negative in front. So this is correct. Okay. With this one, right, radicals often look pretty frightening, but just remember that a radical x can be written as x to the half. So that's really key, because that helps us to follow the same rules we've been following, where the exponent is supposed to go up. So if we think of this, as being written like this, then it becomes a little easier to recognize that we just need to increase the exponent by 1. So now it's 3/2, right? Because half plus 1 gives me, right, 3/2. And then you need to ask yourself, what do I times 3/2 by? That would have given me just a plain 1 in front. What do I times 3/2 by? That would give me a 1 in front. Well, it has to be the reciprocal. And then we can't forget the plus c. So this is our answer. Cool. All right, on to page 5. Okay, cool. All right, so this is like the last topic that is new for the course. This is connected to antiderivatives. And then after this, it's just a review. No new topics. Okay, so here is a very important application for derivative and antiderivative: acceleration, velocity, and position. Okay, so lots of symbols on the page, all just so that you can pick the ones that make more sense to you, not so that you'll be overwhelmed. So all this is saying is that the derivative of acceleration is velocity, and the derivative of velocity is position. Reverse, the integral of acceleration. Oh, I think I said it wrong. Let me restart. When you take the derivative of velocity, you'll get acceleration. Thank you. Pause. Okay. When you take the derivative of velocity, you'll get acceleration. When you take the derivative of position, you'll get velocity. And then in using the inverse of that, when you integrate the acceleration, you'll get the velocity, because the derivative of velocity is acceleration. When you integrate velocity, you'll get position, and that's because the derivative of position is velocity. Okay, cool. So let's show what that looks like. All right, so here we go. So a particle moves along the x-axis with an acceleration. They give us the equation, and then they like to give you these key pieces of information: initial velocity, initial position. Initial means starting. So if it's initial, the time is 0. You'll notice that instead of x now, we're using t because it's time. So it's going to work exactly the same, but we're using t as our variable. Okay, cool. So here's how we do this type of problem. First, we know that that we are going to integrate the acceleration to get the velocity. Cool. So here we go. I'm going to integrate this. So we're going to bring up the exponent. So in other words, we're integrating this. Okay, so bring up the exponent. So it's going to be t to the 3. Double check, 3 jumps down. Okay, so we're fine. Exponent goes up by 1, t squared. What can I times the 2 by? That would have given me 4. Well, that has to be 2. Just to double check, 2 times 2 is 4, down by 1. Okay. And then this just gets a t. Now, here comes this crucial thing, right? We need a plus c. We integrated the acceleration, so we know that this is the velocity. But now we have another piece of information. They said that initial velocity is 10. So that's v of 0 because the time is 0 when you're initially doing something. And then you have, plug these zeros in. It's all going to be 0 plus C, but they told us that V of 0 was 10. So I think we just discovered what C is. So now we can rewrite this with our known value of C. So now we know the velocity function. Okay. Which is great, but we need to talk about the position function. So we are going to integrate velocity to get position. We're going to integrate this function that we just discovered. So exponent up by 1. What could we times by 4 to get 1? Well, it has to be 1/4. Up by 1, t to the 3. What could we multiply by 3 to get 2? What could we multiply by 3 to get 2? It has to be 2/3. Up by 1. What can we multiply by 2 to get 6? Has to be 3. This becomes 10t. Don't forget the plus c. Okay, and that is our P of t, our position of t. Okay, so, okay, cool. So they told us that our initial position is 2. So that means P of 0 is 2. These, when you plug in 0, this whole entire thing is 0 except for C. So we just discovered the C is 2. So that means that when we officially write out our position function, it's going to be all this. And then C is 2. So we found our position function, which they said, what is the position function? But then they also said, what is the position at 1? So the last step for the problem is going to be just to plug 1 in here. P of 1 equals 1/4 times 1 to the 4th plus 2/3 times 1 to the 3 plus 3 times 1 to the 2 plus 10 times 1 plus 2. Okay, cool. So to simplify, 1/4 plus 2/3, I'm just going to do this in a different color. So that's 1/4 plus 2/3 plus 3 plus 10 plus 2. Cool. 3 plus 10 plus 2 is 15. This I'm going to rewrite as 3/12 plus 8/12. 3 plus 8 is 11. So we have 15 and 11/12. Nice. Cool. So to review, we integrated acceleration to get velocity. We plugged in the given information to find what the plus c was. We then integrated velocity to get position. We plugged in the given information to get what the plus c was. That meant we knew the position function, and then we plugged in the requested t value to get an answer. Cool. One more problem. Okay, all right. So similar problem. The only difference here is they didn't tell us an initial value. They told us a different value, which is still going to work in the same manner. Okay, so they gave us acceleration. So we are going to integrate the acceleration to find the velocity. So t to the 2. What can we times 2 by to get 6? It has to be a 3. T pops up here, plus c. That is our v of t. Now, this time they did not tell us initial, but they did tell us this. The velocity is 25 when t equals 3. Okay, so that means that v of 3 equals 25. And it also equals 3 times, right? I'm just plugging in my t here. So 3 times 3 squared minus 2 times t, which at this moment is 3, plus c. Okay? 27 minus 6 is 21 minus c. They told us this was equal to 25. Oh, that's supposed to be a plus. So that means that c must be 4. So to rewrite my velocity function, v of t equals 3t squared minus 2t plus 4. Cool. Okay, so that's my velocity function. Now I am going to integrate my velocity in order to get my position. You always have to write the d of t at the end. Okay, so we're integrating. So t to the 3, 3 jumps to the front. Cool. T to the 2, 2 jump to the front. That worked out nicely. And 4t plus c. Okay, so that's our position function. Now they told us position is 10 when t equals 1. Okay, position is 10 when t equals 1. Great. All right, so p of 1 equals 10. So that's going to be 1 cubed minus 1 squared plus 4 times 1 plus c. 1 minus 1 cancels out. That's 4 plus c equals 10. So c must be 6. So to rewrite my position function, p of t equals t cubed minus t squared plus 4t plus 6, because my c is 6. So I did this part. It says find the position function, but then it also says find v of 2 and p of 2. Okay, I'm going to do p of 2 first because I'm right here. So p of 2 equals 2 cubed minus 2 squared plus 4 times 2 plus 6, 8 minus 4 plus 8 plus 6, 4 plus 8, 12 plus 6 is 18. Cool. Okay, so p of 2 is 18. Okay, so I did that one. And then v of 2, we know that v of t is this. So v of 2 is 3 times 2 squared minus 2 times 2 plus 4. 4 times 3 is 12 minus 4 plus 4. So v of t equals 12. Did all 3 things. Great. Okay, cool. I'll do the challenge problem. It's your call if you want to stay tuned for the challenge problem. So this is the video for this packet, and then I'll post a second video where I go over all the review problems. But please make sure to check this one out and to follow along with all the notes before you try to do any of these problems that correspond to this in your review packet. Okay, last but not least, I'll do the challenge problem. Particle moves along the x-axis with acceleration given by a of t equals cos of t. Initial velocity is 2. Initial position is 5. Find the velocity and position functions and the position a at t of pi over 2. Okay, great. So we're going to integrate the acceleration to get the velocity. Integral of cos of t dt. Well, again, if we don't know, we just go back to our page 2. The integral of cos is sine. Cool. All right, so v of t equals sine of t plus c, of course. Initial velocity is 2. Initial means time is 0. So v of 0 equals sine of 0 plus c. And we can just draw our little sine curve down here. Sine of 0 is 0. So if they said that v of 0 was 2, that means that c is 2. So our final version of v of t is v of t equals sine of t plus 2, because our constant was 2. Okay, cool. Now we need to integrate v of t to get p of t. So we're going to integrate sine of t plus 2. And again, going back, the integral of sine is negative cosine. Okay, cool. So don't need that integral sign anymore. So the integral of sine is negative cosine of t plus 2t plus c. And this is our position function. It's messy. Okay, cool. They told us initial position is 5. So p of 0, they told us was 5. So now we bring this down. Negative cos of 0 plus 2 times 0 plus c. Okay, well, if you sketch out, this is cos. So cos of 0 is 1, and there's a negative sign here. So negative 1 plus 2 times 0 is 0 plus c. They're saying that equals 5. Move the 1 over. So your c is 6. Okay, so that means that p of t is equal to negative cos of t plus 2t plus 6. I'm running out of room. Okay, so far we found the velocity function. Here it is. We found the position function. Here it is. And now they want us to find the position at t equals pi over 2. Okay, so let's plug it in. So p of pi over 2 equals negative cos of pi over 2 plus 2 times pi over 2 plus 6. Okay, cos of pi over 2, going over to our little picture of cos, it's 0. Cool, so this is 0. So we've got 0 plus, these 2's cancel out, pi plus 6. So our answer is pi plus 6. All right. Cool. So that was just a challenge problem, just for anyone wanting a challenge. There's not going to be a bunch of tricks with trig or ln's or e or anything like that on the final, because I believe in only testing what we're actually trying to test, which is calculus. So please don't be like stressed if you don't understand that challenge problem. But please do make sure that you understand these other 2 problems. Have a wonderful day.